Hi juniors, in this video we're going to go through two topics. We're going to talk a bit about gases behaving as solutes, and then later on we're going to discuss the effects of temperature on the solubility of solids and the solubility of gaseous solutes. So first, gas solutes. Well, what we want to do is separate out gas solutes from their solid and liquid cousins. As you can see here in the first bullet point, pressure is not going to affect the solubility of a solid and liquid solute. That's essentially because solids and liquids are not compressible. If you squeeze the system, you're not going to get solids or liquids to go more into the solution. However, if you apply some pressure to the system, you will be able to get a significant change on the solubility of a gas. Right? As you squeeze that system, you would be able to force more gaseous solute particles into the solution. Now, where does this matter? Maybe we can think about some important examples of gases acting as solutes. Well, here's one that's not so important. Maybe that soda that you might be drinking right now. The gas there, of course, is carbon dioxide. It's not carbon monoxide. Coca-Cola's not trying to kill you. It's carbon dioxide being dissolved into water to make soda water and give it that fizz that we like in our soda. How about maybe if you're a fish, you might like the fact that O2 is dissolved in water. Right? So gaseous O2 gets dissolved in water, and you can breathe underwater. Or perhaps, maybe for you and I, how about oxygen in the liquid of that's present in blood? Right? The oxygen can transport to the different parts of our body and get used as needed. So the role of gases behaving as solutes can be very important in many. All right, so here's a cartoon that just kind of shows you how it is that we can see the solubility of gases going up as we apply some pressure. So on the far left here we have a system with the piston is held fairly high up, so the amount of pressure, relatively speaking, is somewhat low. As we push down on that piston, we can see that more and more of the purple ping pong balls that are the gas solutes are getting forced into the solution. Apply even more pressure and we can see that we get more and more gases into solution. So to put it quite plainly, as the pressure goes up, the solubility of a gas, okay, is going to go up. Now, this behavior, this connection between pressure and solubility, is in fact quantified by an English chemist named Henry. And as a result, we have Henry's law. Now, Henry's law is articulated in a couple of different ways, depending upon how one textbook likes to do it over another. Sometimes it's written in the first way I show here, P equals Kc. Sometimes it's written as C equals Kp. But the take-home message is that, as you can tell from these equations, there's a direct correlation between pressure and concentration. Both of these equations are sort of the y equals mx portion of a linear relationship. Okay? Now, K here is called the Henry's law constant, and it's a little k. We're going to see throughout the course that the letter K gets used an awful lot excuse me, for constants. K, in fact, is the Boltzmann's constant, but that's not what it's being used for here. K is its own thing in this context, the Henry's law constant. And the thing we want to understand about K is that really it is a property of a solute-solvent combination. All right, so a particular gas trying to be dissolved in a particular solvent will have a Henry's law constant. If you change the gas, you change the constant. You change the solvent, you will change the constant. So Henry's law constants apply to the solute-solvent combination. Now, whether you write it P equals Kc or C equals Kp, the only difference is going to be the units of the Henry's law constant. In this first version on the left, K is going to have the units of pressure per concentration. On the one on the right here, K would have the units of concentration per pressure. So And it really doesn't matter which one you use. Again, it's a linear relationship, right? There's a direct proportionality here. Now, there is a limit to Henry's law. Namely, the only thing that should be going on in order for Henry's law to hold is the gas is simply being dissolved into the solvent. No additional chemistry should be going on. No bond breaking or bond making should be going on during that dissolution process. For example, if I had HCl gas and I was trying to dissolve that in some water, well, what's going to end up happening is I'm going to make H plus in the aqueous phase and Cl minus in the aqueous phase. In other words, I'm going to be doing some chemistry. I'm going to be breaking some bonds. So for HCl in water, it's not going to behave in a linear relationship predicted by Henry's law. So Henry's law doesn't work really well for this particular situation. But if we're talking about gas solutes like, say, oxygen or maybe nitrogen, which don't do any bond breaking or bond making other than intermolecular forces with the solvent, Henry's law constant will hold pretty accurately for these types of systems. Here's a practice problem for Henry's law. I'm not going to do it here, but why don't you take a few minutes when you have a chance to do it. The answer you should get for the solubility of O2 should be about 2.0 times 10 to the minus 4 molar. See if you can get that answer on your own when you have a chance. Okay, so that's pretty much it when it comes to gas solutes in a solvent. We have Henry's law. It works pretty well in many cases, but not in all cases. We'll talk a little bit more about gas solutes in 2 more slides when we talk about temperature. We'll get to that in a minute. So, temperature. Let's talk about temperature. So I'm showing here a chart that shows the solubility versus temperature for a number of different solutes. As you can see on the chart, all the solutes that are being shown would all have started at in the solid phase at room temperature. Potassium nitrate, sodium nitrate, sugar, potassium chloride, all of these would be solids at room temperature. So we're really looking at, in this particular case, the solubility of solids in water, right? We're talking about water being the solvent. Now, as you can see clearly, for most situations, the solubility of the solid is going up as the temperature goes up. So, what does that mean? What implications can we draw from that? Well, let's take a look at a specific example. I'm going to look at, let's say, potassium nitrate. What happens when you throw potassium nitrate in water? What does it actually do chemically as it dissolves? So you have KNO3 in the solid phase, and we're going to dump it into some water. Now, that's a 2. What does it do? If you dissolve a salt into water, what you of course get are the aqueous ions. So here's the reaction that we'd be doing. Okay? So we're breaking the ionic bond there. Remember, we talked about this in class. If I dissolved a covalent compound like sugar, I wouldn't be doing any bond breaking or bond making, right? I would just be dissolving the sugar without disturbing any covalent bonds. But back to potassium nitrate. We see here that the solubility of potassium nitrate goes up as we add heat, as the temperature goes up. So what might that mean about the thermodynamics, about the role of heat in this system? Well, notice that we have here, and just so I can highlight it, let me pick a different color here. Notice that I've written this intentionally as an equilibrium. Right? When you dissolve a salt in water, it's going to go back and forth between being in the solid phase or being in the aqueous phase, especially once it gets to a saturated solution. Some of the potassium is KNO3, some of the potassium is K plus aqueous. So we have an equilibrium going on in this system. So what does that mean about the role of heat? Well, as the temperature goes up, the solubility increases. Which side of this equation is being favored then as temperature goes up? As temperature goes up, the ions are being favored. We favor the right side of the reaction. So, hopefully you're picking up on the hints I'm trying to drop here. Whose concept are we alluding to when we talk about changes in the equilibrium as we do things like change temperature? Hopefully, you remember this guy's name, Le Chatelier. Or, since we're Americans, we would say Le Chatelier's principle, right? So, we have a perturbation, we change temperature. In the case of potassium nitrate, that causes the equilibrium to shift again towards reactants. So that must mean that in this system, heat is behaving as a reactant. And if heat is behaving as a reactant because when we add heat, right, it shifts towards the product side, that must mean that this reaction is endothermic. So I'm going to represent the heat here as another reactant. I'll put a plus delta. Delta is a symbol often used for heat. So heat is a reactant. If you add heat, it shifts to form more ions in solution, so the reaction must have been endothermic. So all the blue lines you see on this chart going uphill, all of those would have heats of solution that are positive, that are endothermic. Meanwhile, things like sodium sulfate and cerium sulfate have exothermic heats of solution. Their solubility drops as you add heat. So they get pushed back to the left of the undissolved solid solute. So here's a couple of thermodynamic ideas coming together, right? We're still talking about heats of solution, but now we're reintroducing the concept of Le Chatelier's principle in this context. All right, how about gaseous solutes? Here's another chart showing the solubility of some solutes versus temperature. All of these solutes, as you can see, methane, oxygen, carbon monoxide, nitrogen, all of these solutes are going to be gases. And you see that they're all in red, like cerium sulfate was in the previous chart, indicating that their solubility is dropping as the temperature goes up. So, if the solubility drops as the temperature goes up, that must imply that the delta H of solubility for all of these gases is in fact negative. Okay, they're all negative, so they're exothermic. So, for example, take oxygen gas, introduce some water, you get the equilibrium, so you form O2 aqueous. Notice I didn't break any bonds because oxygen is a molecular compound. No covalent bonds are broken in the process. And since this is exothermic, I would put heat as a product. So I increase temperature, I add heat. That causes the reaction to shift back to the left, forming more free oxygen. Not dissolved oxygen, but free oxygen in the gas phase. So why is it then that gases all produce this negative heat of solution? Well, let's think about our different steps for making a solution. We talked in class about delta H1, delta H2, and delta H3, and we simplified it down to delta H1 and delta H of hydration. So let's think this through about delta H1 and delta H of hydration for a gas. So here's the energy of my gas and my water. And I'm going to do delta H1. How much delta H1 does it take to expand a gaseous solute? The answer is very little, because the gas is already expanded. So the magnitude of my delta H is going to be very, very small. In fact, it's probably even smaller than that tiny little arrow I just drew. So delta H1, the expansion of the gaseous solute for a gas, is going to be very small. Now, do you remember from class what the sign of delta H of hydration always is? It's always negative. So the delta H of hydration always causes the energy of the system to drop. Delta H of hydration causes the energy of the system to drop. So, since delta H1 is always very, very small for a gas, you don't go up very much. Then when you do the delta H of hydration, you come down quite a bit. And so the net result that I'll show in a different color just to highlight it, the net result right there is that you're always going to have a delta H that's negative for the heat of solution of a gas. Right? Every single one of them has a delta H that's negative because you don't need to expand very much. All right, so there we have it. There's a little bit of quantification through Henry's law on gas solutes, a little bit of a trend for looking at the solubility of solids in water as we change the temperature, and we can use Le Chatelier's principle to understand it, and we can use Le Chatelier's principle and the thermodynamics of solutions that we developed in class a few days ago to understand that for gases, the heat of solution is always going to be negative. All right, we'll leave it at that.